Well, as Bo said, it is a tough day to miss. But I want you to write this down up top. Uh, the definite integral bounded from a to b of f of x dx. This refers to the area bounded by the curve in the x-axis from a to b. And there's some calculus behind that and how we can make it work out. But there's two types of calculus. There's the very involved one, which is adding up an infinite number of rectangles, and then there's a shorter way, which we'll show you later on. But this is equal to the limit as n goes to infinity of the summation from I equals 1 to n. Now, I want you to, this is the part I really want it to be in your brain. I don't want you to look at this just see gibberish. I want you to be able to think about this. Forget about the limit piece. Just when we have been doing these rectangle problems, we've been taking the width times the sum of the heights. So we're going to sum the heights. How do we sum the heights? We plug the x values into the function, correct? So f of x sub I, that's the sum of the heights, and then you multiply that by the width. Delta x is the width. And how many do we add up? We add up an infinite number of them. That's what we're doing. And in this situation, we do say that delta x is equal to b minus a divided by n, and x sub I is equal to a plus I times b minus a over n. Yes. And tomorrow you'll have a lot of homework on it. Tonight, just 2 practice problems, and then tomorrow you're expected to be excellent at it. Yep. So after you see the example today and you practice, I'm confident that you will be good to go. All right? What? You'll have about 15 minutes. Okay. So we are not going to do 4 rectangles, and we are going to switch the problem. Instead of doing x to the third, we're going to do 2x to the third, so you can see what happens when you have a constant, how much changes. But again, this shape, 2x to the third, looks something like this. Okay? And we're bounding it from 0 to 3, and we're going to look at that area. Okay? That's what we're doing. So the question is, what would be the width if I had 3 rectangles? 1. What would be the width if I had 6 rectangles? A half. What you're doing is you're taking the end point minus the beginning, and you're dividing by the number of rectangles. Question? Yes, we'll do where the beginning is not 0 tomorrow. So, in this situation, it says, what is the width of n rectangles? The way we calculate that is we take b minus a divided by n. So, width of n rectangles would be your delta x. And we find that by taking 3 minus 0 divided by n, which is 3 over n. You must be clear how we got that. That must be absolutely confident that you could do that every single time. Is there any question on it? Okay, then please watch the next one, because this is where people get confused. And you may wonder, why are you so intent about this, Mr. Guinness? Because the first time I tried teaching this, nobody understood it. So it takes years of practice and trying to explain this correctly for people to really get it and understand it, okay? So suppose I were to divide this up into 4 rectangles. This would be 3 halves. That spot would be 3/4, and this spot would be 9/4, okay? So as you look at this interval here, and I'll draw it a little bit more plainly, if we want to be able to evaluate the heights, and we start at 0, we go to 3, and again we have 3 halves, 3/4, and 9 halves. 9/4, excuse me. So as you look at that first interval, okay, and we draw a right-hand rectangle, where do you evaluate the height? 3/4. For your first rectangle, you went over how many widths? One width. For your second rectangle, you evaluate at what? 3 halves. You went over how many widths to get there? 2 of the widths. You went from 3/4 to 6/4, or 3 halves. And then how many widths do you go over to get to 9/4? 3. 3/4 plus 3/4 plus 3/4 is 9/4, correct? And then finally 12/4. Okay, so this is your first one, your second one, your third one, and your fourth one. Well, we don't want to do 4. How many do we want to do? So we need to apply the same type of reasoning, but in a more abstract way. So what we do is we start at our beginning. We start at A, and we add on a certain number of widths. So I'm going to add on widths. Katie, how many widths do I add on? I, whichever rectangle number you're working on at that time. Does that make sense? Now, so far, as Kimball said, we've always started at 0, and we're going to start at 0 again today. But tomorrow, we're going to start somewhere else. Okay? So, in this case, I just have 0 plus I times, and we've already decided B minus A over N. It's 3 over N. So when you multiply that, you get 3I over N. So that determines the position at which we evaluate the heights. Does that make sense? So now we just plug it in. So it says express the area as a definite integral and as a limit of a Riemann sum. You say that to normal people in this world, and they're like, holy cow, you must be really intelligent. In fact, you even say it to math people, and they're like, wow, you really know what you're doing. You're putting yourself kind of in that top 5% of the population right now of people who have done this stuff. You know what I mean? Not a lot of people have added up the area of an infinite number of rectangles. Do you like to differentiate yourselves? I think so. So we're doing something. It's putting you a mark above the rest. How does that make you feel, Amber? All right. Well, let's do it. Take the problem. Integral from what? 0 to 3 of the function 2x to the third dx. So the dx represents the width, and then this is the sum of the heights from 0 to 3. Okay. The width. It's like, you know how we have delta x? They're using dx, okay? And so you could think of it in that way. Is equal to the limit as n goes to infinity of the sum from I equals 1 to n. What are we going to add up? We're going to add up an infinite number of rectangles. But what part of the rectangles are we adding up? We're adding up the heights. And we calculate the heights by taking the position, 3i over n, and plugging it into the function. So our function is 2 times x to the third, so 3i over n to the third. So that will generate our heights times delta x. What's delta x? Times 3 over n. So I have the limit as n goes to infinity of the sum from I equals 1 to n. It's so fun to write that. And then let's just come up with a little bit better representation here. What is 3 to the third? 27 times 3 is 81 times 2 is 162. I to the third over what? N to the fourth. Now, what we like to do here is all we're doing now is we're just evaluating an infinite limit, which is child's play. We've done that before, right? I mean, we've made a mockery of that. I mean, we've shown ridiculous times where it exists, it doesn't exist, and we've come up with 2, we've come up with 8, we've come up with infinity, we've come up with all sorts of stuff. Well, all we got to do is we got to get rid of this I because n is going to infinity. So let's factor out everything that doesn't have an I. So we have the limit as n goes to infinity of 162 over n to the fourth times the sum from I equals 1 to n of what? I to the third. Now, we wouldn't have time before lunch So right after lunch, I'll show you again a mathematical induction problem. Just take 5 minutes, okay? 4 minutes, and then you'll be able to work. But we've learned that this summation, we did this one last year. Look it over on the board. If you have the sum of just I, it goes to n times n plus 1 over 2. If you have the sum of I squared, n times n plus 1 times 2n plus 1 over 6. And if it's I to the third, n squared times n plus 1 squared all over 4. So that is my summation. If you don't believe that those are true, we can prove them. Um, yes, I do know, but the question you're asking is rather involved. So if you notice, I could give you a lot better reasoning. Notice that I to the third is simply I squared. You square the n plus 1, you square the 2. So that's part of what I could tell you. But as far as why it is 6, it's really a method of counting. And I would have to make a counting argument for you, which we could do. It's just it's not going to work very well right now. So anyway, this is the sum. So all I do now is substitute a known sum. So we have the limit as n goes to infinity of 162 over n to the fourth times, and instead of that summation from I equals 1 to n of I to the third, we're simply going to plug in n squared times n plus 1 squared all over 4. Do you see this? Excuse me. That's a substitution I made. On the board right there, it's written down. No, I've got an I to the third. Yesterday, were you here yesterday? Okay, yesterday we had, I'm sorry, I didn't mean that to sound mean. But the I squared, see how we have the I squared? Yesterday we plugged in I squared, right? Just depends on what's happening with the I. So I squared is n times n plus 1 times 2n plus 1 over 6. That's what we did yesterday. Is that better? Okay. We blew it up. Here we go. Let's do it. This is child's play, folks. All we got to do is do the limit. The limit. Our I's are gone. All we have left is n's. Just now it's just algebra. So we got 162 times n squared times n squared plus 2n plus 1 all over 4n to the fourth. And then I'm going to distribute my n squared to my 162. So let's come up with a polynomial at the top. What do I got? Yep, 162 n to the fourth. And 24 n to the third. 162 n squared. All over 4n to the fourth. We know how to do infinite limits. We take out the largest degree in the top and the bottom. So we'll take out an n to the fourth. We get 162 plus 324 over n plus 162 over n squared all over 4n to the fourth. Oh, this is the exciting part. We're letting the limit go to infinity in order to sum the area of an infinite number of rectangles under a finite space. I just have you just think about that. Okay. N to the fourth, gone. What happens to 324 over n? 0, 0. We get 162 over 4, which is 81 over 2, or 40.5. Booyah! And in case you aren't impressed, we could type it in 2x to the third into our calculator. Go, second calculate, grab number 7. Our lower limit is 3. Our upper, whoop, or 0. Our upper limit is 3. And it will draw the rectangles for us. And boom, 40.5. That is, I mean, that is, oh, Sini's not impressed. First of all, she shows up late to class. And then, yeah, that's a forged pass. Very nice. And second of all, she's not impressed. Now, guys, I get it. Like I said, I don't listen to the Beatles, but I understand why they're great. I don't expect you to love that, but you got to understand why that's so stinking impressive. I mean, this is what we did. This is beautiful. This is just one. Yeah, get out of here. Go eat some lunch. We'll come back and just bask in its glory. Okay, I want to give you guys some time to practice, but real quick, just want to finish up where we were at. This formula up here, you guys do see where these parts come from, correct? This delta x will give you your width. This x sub I will give you the spots to evaluate your heights. And you do understand why it's so cool, right? Again, as you state what you are doing, you're adding up the area of an infinite number of rectangles in a finite space. And we did it, okay? So it's going to take you a little while to really try to fully grasp what we did. Um, Stuart Bailey, you guys remember Stuart at all? I remember he walked out of class the first time. Second time we did it, it's kind of like, okay, what's going on? But the third time, after the third day, he walked back and he said, he said, I was working through it last night. After I practiced a few problems, I finally did my third one a little bit more slowly. I really looked at it and understood all the pieces. And he said, it was the most beautiful thing in mathematics I'd ever seen in my life. So it's fun to hear that come from students. So you ask what makes me so excited about math sometimes. This piece right here, I just think it is awesome. It truly is awesome. So do this for time. Yeah, I'm sure it would be. I get a lot of applause for it. Okay, so here you go. One example of mathematical induction so you can understand. So this is for Taylor Willis and others who, it's like, how do we get that stuff? So you show true for like case 1. So what does the number 1 add up to? 1. And if you plug in case 1 and divide that as such, you get 1. Now we'll do 2 numbers. 1 plus 2 is, so does that equal 2 times 2 plus 1 over 2? Are you convinced it's going to work? Well, assume true for k. So 1 plus 2 plus 3 plus dot 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 plus k is equal to k times k plus 1 over 2. So here's the deal. We are going to show true, or 3, excuse me. Assume true for k plus 1, such that 1 plus 2 plus 3 plus dot 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 plus k plus 1 is equal to k plus 1 times k plus 1 plus 1 over 2. So that's what I'm going to do very quickly right now. Do you remember doing this now last year? So, look, thank you. You stole the words out of my mouth. So I'm going to use my inductive hypothesis right here. So what does this equal? K times k plus 1 over 2 plus k plus 1. I'll write that over 2, so k times k plus 1 plus 2k plus 2 over 2, right? So that would be k squared plus 3k plus 2 over 2. Is that factor? K plus 2 times K plus 1. And so I could write over 2. So I could write this as K plus 1 times K plus 1 plus 1. So that's K plus 2 over 2. And is that what I have on the right-hand side? Yeah, so this is a very quick math induction, which you did last year, so we've shown it's true. So we showed it was true for 2 terms. So now that I've shown it's true for K plus 1, what's the K plus 1 term? 3. So if it's true for 2, it must be true for 3. Well, now I've shown it's true for 3. So if it's true for 3, then it's true for 4. Okay, now I show it's true for 4. So if it's true for 4, it must be true for 5. And it keeps on going, okay? So that's why we've shown, so it works out. So that's the deal, okay? So you asked about the math induction. We don't have to redo the math induction. We just simply use those rules. They are true. What I want you guys to do right now is your homework. You have the rest of the hour to work on. And tomorrow, you're going to get a lengthy homework assignment. But right now, I just want to give you very straightforward basic problems. Sure, say hi to Megs.
Hi, Megan. It's Teeny. Hi, Megan. It's Taylor. We miss you. Hi, Megan. It's also Seeny.
Hi, Megan. You better have got 1,000 points last night.
Just turn off.
Hi, Mac.
Hi. Megan, this is Mr. Gantz, and out of all these people here, know that I miss you most because you bring the most to math class. Trying to get through this stuff without you, it's like they know nothing. They know nothing.